We all know earthquakes are one of the most powerful forces on the planet, right? But how do you actually measure something that can literally shake the entire world? Well, today, we're going to dig into the story of the revolutionary invention that finally gave us a way to understand the power shaking the ground right under our feet. I mean, think about it. How do you measure an earthquake? How do you possibly put a single simple number on something that can wipe out a city in just a few minutes? For decades, this was a massive puzzle for scientists, and to even get started, they needed a whole new field of study. And that field is seismology. It's the science of tracking those seismic waves, the vibrations that shoot through the earth when a quake hits. But see, just tracking the waves, that wasn't enough. The real challenge was figuring out how to measure them, how to compare them in a way that actually made sense. Okay, so let's jump back in time to the early 1900s. Scientists, or seismologists, had these instruments called seismographs that could, record the Earth's movements. But they had this one huge problem. They had no universal, no mathematical way to say, hey, this earthquake was this much bigger than that one. The only system they had wasn't based on instruments at all. Nope, it was based on something way less reliable: what people saw. Yeah, this old system was called the Richter Scale. And look, it was a decent first try, but at its core, it was basically a scale of opinion. It wasn't about objective measurement at all. So the Mercalli scale measured what they called intensity, and it was all based on what you could see. Did pictures fall off the wall? Did the chimney crumble? You can probably see the problem here, right? The amount of damage totally depends on where you are. A medium-sized quake in a big city could look way more chaotic than a monster quake out in the middle of a desert. It was just completely unreliable. And this is where our main character, Charles Richter, steps onto the scene. He was a physicist working at the Caltech Seismological Lab, and he saw this problem crystal clear. He just knew science needed something better, something that wasn't just based on what people happened to see. So the goal became super clear. They had to move from subjective to objective. They had to get away from looking at damage and instead rely on pure math. What they needed was a single, absolute number for an earthquake's magnitude that would be the exact same no matter where on Earth you measured it from. And the solution? It came from Richter working with his colleague, Dr. Gutenberg. The two of them were poring over data from hundreds of earthquakes, trying to find some kind of mathematical pattern. But right away, they hit a wall. See, the difference in energy between the tiniest tremor they could detect and the biggest quakes ever recorded was just enormous. So when they tried to plot all that data on a normal graph, the numbers were literally flying off the charts. There was no way to see it all in a way that made any sense. And this was the big aha moment. Dr. Gutenberg had this brilliant idea. He suggested, hey, let's stop thinking in a straight line. Let's think logarithmically. And that one suggestion? It was about to change seismology forever. So what exactly is a logarithmic scale? Well, here's the key. Instead of each step up being a simple addition, like 1, 2, 3, 4, each step is a multiplication. So on this new scale, a magnitude 2 earthquake isn't just a little more powerful than a 1, it's 10 times more powerful. And a magnitude 3? That's 100 times more powerful than a 1. This was the secret to finally taming all that wild data. Okay, so with this new tool in hand, the path forward was obvious. They plotted hundreds and hundreds of earthquakes, and what did they find? Logarithmically, they all followed pretty much the same pattern. So from all that data, they created one single standard curve. Now, whenever a new earthquake happened, all they had to do was compare its data to that standard curve, and boom, a new objective scale was born. And just like that, this new standard was introduced to the world. For the first time, scientists everywhere had a common language to talk about the true power of an earthquake. So in 1935, the scale, the one that would bear Richter's name, was officially unveiled. Now, it's true that today seismologists often use even more advanced tools like the moment magnitude scale. But the basic idea, that fundamental logarithmic principle that Richter and Gutenberg came up with, it's still the foundation for how we measure earthquakes to this day. All right, so we know how the scale was made, but what do these numbers actually mean for us, living on this constantly shifting planet? Well, the scale reveals some stuff that is truly mind-boggling. Take a look at this number, 9,000. Any guesses what that is? I'll give you a hint.
It's something that happens every single day, and it's all about earthquakes.
Yep, that's right. 9,000 is roughly the number of earthquakes our planet has every single day. Now, most of these are below a magnitude 3, which means they're so small we don't even feel them. It just goes to show you how incredibly sensitive this new scale really was. And this is where you can really see that logarithmic power in action. A moderate quake, say a magnitude 5, one that can actually cause some damage, that releases about 1,000 times more energy than those little daily tremors. But a major quake, a magnitude 7, we're talking nearly 1,000,000 times more energy. The jump in power is just staggering. And that, of course, brings us to the really big one. This number right here. This represents the most powerful earthquake ever recorded by our instruments. Back in 1960, a magnitude 9.5 earthquake absolutely rocked Chile. The energy it unleashed is almost impossible to imagine. It's exactly this kind of massive, cataclysmic event that the Richter scale was designed for, to give us a way to mathematically wrap our heads around a force that is almost incomprehensible. But this also leads us to a pretty sobering reality. We've gotten incredibly good at measuring earthquakes with amazing precision, but we are still completely at the mercy of their power. To this day, there is absolutely no device, no invention that can stop an earthquake from happening. Which leaves us with one final big question. We've come so far, right? From just looking at cracked walls to having logarithmic precision. We can measure them, but we can't stop them. So, where does the science go from here? Is it all about prediction now? Better early warning systems? Well, that's the massive challenge facing the next generation of scientists.